15.19. Write the equilibrium law for each of the following gaseous reactions in terms of molar concentrations. All right, so for this problem, it's going to be important to have the equilibrium law, which is written out as follows. Basically what we have is we have the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. And so for problem, for number 1A, it is going to be as follows. What we have here is 2 PCl3 plus oxygen yields 2 POCl3. So we've taken the concentration of the POCl3 right here, and we raised it to the second power simply because of its coefficient right there. And then same thing with the reactants. We've got PCl3 raised to the second power because the coefficient listed in the reaction. And then oxygen is raised to 1 power, which is assumed also because of the coefficient. So for problem B, the Kc value is going to be as follows. Raised to the second power, we get that from right there. Divided by, so we've got the products divided by the reactants. So this is pretty straightforward, and we're just going to keep doing this for all of the problems that are given. So wrong one. And then for D, it's going to be as follows. And then the last one, this is chemistry at its best right here. Basically, once you get the handle for one, it's just like, it's the same thing, plug and chug. So there we go. Write the equilibrium law for the reactions in problem 15.19 in terms of partial pressures. All right, so we're going to follow this outline right here for finding the Kp, which is the partial pressures of the gaseous reactions. And so it's pretty much the same, except we're going to take into account that this is partial pressures, and so we're going to signify that with P's. But I mean, it's the same information, same data. So coming over here to the first one that we had, where it was, this was the Kc. I guess the Kp is going to be the exact same thing. We'll just have Kp equals partial pressure of So you can see they're pretty much exactly the same. We're just recognizing this as partial pressures. So you'll be using this same idea for the rest of the reactions in this problem. And if you have any questions, check the back of the book, because they won't lead you astray. So that is it. 15.23. Write the equilibrium law for each of the following reactions in aqueous solution. Okay, again, we're going to be using, this is our guide, just products over reactants, and each concentration is raised to the coefficient found in the reaction given. So over here with part A, we're just going to go ahead and take our products, and here we go. So it'll just be Ag NH3 squared plus, and notice that there's no coefficient there, so we're done with that. Reactants is just going to be Ag times NH3, and this has coefficient of 2, so we're going to raise that to the power of 2, and that's that for that one. For this one, part B, we're just going to, no coefficient here, so it's just going to be our product. Over our reactants. And notice there's a 4 there, so we're going to put a 4 exponent right there. And that's it for this one. At 25 degrees Celsius, Kc value equals 1 times 10 to the negative 85th for this reaction. What is the Kc value of the following reaction? All right, so one important thing, this is our reaction that they gave us, and this is the Kc value that they gave us. And then they want us to find the Kc value for this reaction. So what you notice, first off, is that it's actually the reverse of the initial reaction. So when that's the case, we're just going to take the inverse of the Kc. So for the reaction that they want us to find the Kc value, it's actually 1 over 1 times 10 to the negative 85, which just equals 1 times 10 to the 85. So that's going to be our Kc value for the second reaction. And that's how you do it. You just take the inverse, and because you recognize that the two reactions are opposite of each other. Pretty straightforward. 5.27, write the equilibrium law for each of the following reactions in terms of molar concentrations. How does Kc for reaction A compare with Kc for reaction B? All right, so at this point you should be pretty familiar with the equilibrium law. Pretty straightforward. I'm just going to write this out for this reaction. Equilibrium law for this one is going to be products HCl. And just because the coefficient is 1/2, don't let that scare you. You just write it out like this, and remember that actually when you raise something to 1/2, that's actually the square root. So and so for part B, they want us to compare how the Kc values differ for both of these, and what do you notice? And as I mentioned earlier, 1/2 actually, as an exponent, refers to the square root. So this would actually be the square root of the concentration of Cl2 times the concentration of H2. And so, anyways, looking at these two, you can see that the Kc here is actually equal to the square root of Kc, just by simple multiplication. If you square everything here, all the exponents, you're going to end up with this. So Kc for B is actually, the square root of that is actually the Kc. That was A, for Kcb. So there you go. .29. A 345 milliliter container holds NH3 at a pressure of 745 torr and a temperature of 45 degrees Celsius. What is the molar concentration of ammonia in the container? All right, so for this one, we're going to use the ideal gas law, which is just PV equals nRT. So they asked for the molar concentration, and so the molarity is just number of moles divided by the volume. So what we have right here, we're just going to rework this and solve for, we want N over V. So this was basically like N over V. So if we've got that, we'll just go N over V equals P divided by RT. And they gave us the pressure, the R is just a constant, and T is temperature. So now it's just plug and chug. So molarity is just going to equal, they said it was 745 torr. And we're just going to do a quick conversion there to ATM because the R value is in ATM, so that's what we need. And then the R is just 0.0821 liters ATM over mole per Kelvin. And they, when we convert the temperature to Kelvin, it is 318. So our units are going to cancel, and we'll end up with 0.0375 molar concentration. For which of the following reactions does Kp equal Kc? All right, so for this problem, what you're going to want to use is you're going to want to use this equation, which is found on page 705. And basically it just relates the Kc value to the Kp. And as you can see, we want the problem asks for which equation is Kp equal to Kc. And so in order for that to occur, we need this right here, this part of the equation, to equal 1. We want that to equal 1. And so the way that's going to happen is if we take the N, delta N, which stands for the change in moles of gas, if that equals 0. So really we want, in order for that to happen, change number of moles of gas has to equal 0, because anything raised to a power of 0 is going to equal 1. And so this will equal 1, and really we'll be left with Kp over Kc, or Kp equals Kc. So for, I'll just walk you through example 1 that they give us. And this right here, the change in moles of gas. What we're going to be doing is we're just going to be looking at the coefficients given. And remember that change, it's always final minus initial. So in this case, products minus reactants. And for this, our reactants, we just have 1 mole of gas. So that'll just be 1. Over here, we have 1 mole of gas plus 2 moles of gas. so that equals 3. So 1 minus 3 equals -2. And so if we were to plug this -2 back into this equation, this value right here, the RT, would not equal 1. And so that is not going to give us a Kp equals Kc. For problem B, we do have that case. The number of moles of gaseous products is 2, and same with the reactants. So that's going to equal 0. When we plug 0 back into change of moles of gas, this is going to equal 1. Kp is going to equal Kc. In number 2, we've got, it'll be 2 minus 3, and that equals -1. So that doesn't work. So problem B, or equation B, is going to be the answer.
(15.33) The reaction shown here has a Kp of 6.3 times 10 to the -3 at 225 degrees Celsius. What is the value of Kc at this temperature?
Alright, so what we're going to do here is we're going to be using the same equation that we found on page 705, and it's just relating the Kp value to the Kc value. Alright, so alright, and we're looking for the Kc value. They give us the Kp, R is a constant, T is temperature, and this is just the change in moles of gas. So if we work this equation, we're going to get Kc is equal to Rp over R times T Kp, thank you, Mg. All right, so if you just plug in the values right here, it's going to be, the Kp they told us was 6.3 times 10 to the -3. R is a constant, 0.0821 liters ATM per mole times Kelvin. And at 225 degrees Celsius, that converts over to 498 degrees Kelvin. So when we do this math, just straight across, important thing, this right here, this bottom, we need to multiply that times the change in number of moles of gas. So we're going to come up here to the equation, and we see that we've got 1 mole of gas as the product, and 2 plus 1 equals 3 moles of reactant. So that gives us a -2. So this whole term on the bottom is going to be raised to the -2. And then when we do the math across, we just get 11 as our answer, and that's going to be the Kc value.
(15.35) The reaction shown here has a Kc value of 4.2 times 10 to the -4 at 500 degrees Celsius. What is the value of Kp at this temperature?
Alright, so for this equation, one last time, we're going to be using the equation on page 705, equating the Kp to the Kc. So I'll write that out, just so we're all clear. Kp is equal to Kc times Rt to the change in number of moles of gas. Alright, and they give us the Kc right here. This is very helpful. So we'll just plug that in. 4.2 times 10 to the -4 times Rt. R, 0.821 times, they said 500 degrees Celsius, which equates to 773 degrees Celsius. So, or Kelvin, 773 degrees Kelvin. And we're going to raise the RT to the change in number of moles of gas. And this is where we use our reaction that they gave us. We've got 3 as the product, so 3 moles of gas here, minus 2 moles of gas here is the reactants. That's going to give us 1. So we're just going to raise that to 1. And when we do that math across, we're going to get 5.4 times 10 to the negative 5 is our answer.